Thank you very much. There will be a quiz at the end about the handbook of robotics. So be ready. Okay, so I thought before the talk, everyone mentioned the robotics center. I'm glad Harry was there, and we were just talking about it. I thought I will share with you a few slides about the new Stanford Robotics Center. So robotics is multidisciplinary, everyone knows. And everyone is trying to address some aspect of the problem. However, it's very often that it's very difficult to find the environment where people can work really together. So this idea of multidisciplinary research in robotics is the guide line for what we have done at Stanford with the Stanford Robotics Center. The idea is to create an environment where people can work together. It is not a collection of laboratories where we are all under the same roof. It is really about the project. And the space, it belongs to no one except the project, the challenging project that cannot be done in our laboratories. So we get a great team of researchers, and this is done at the level of the university. So we have different schools involved, medical schools, sustainability, and we have most of the people you know in robotics developing, working in robotic and contributing to it. And Harry just mentioned Steve Cousins. Steve is the executive director working with me on leading this big effort. So what is robotics? And this is the problem we're facing today. Sometimes we think robotics is one angle of like going and running some algorithms to find how humans move, and then we can get that thing working on the robot. Actually, there is a lot of knowledge that is needed behind robotics. Everything we are doing with robots involve mechanisms that need to be designed, and that need to be designed for the goal in the impact. But in order to design those different instantiation of the robot, we really need to have the knowledge, and we need to know about what kind of interaction and what kind of applications. And this is the problem that we are facing today, that somehow we are missing a lot of the knowledge, and we are going directly to the application and without really the foundations that are necessary to work with robotics. So this is something that we are trying to bring together in the center. And as I said, the laboratories are bringing a lot of contributions to the core robotics. Now, if we are building capabilities that are general enough, those capabilities can be directly applied in different fields, in medical robotics, in field robotics, in all these areas. We are not going to engineer solutions to specific areas. We are taking almost the same frameworks. What is robotics? It's about perception and action and thinking and reasoning about all of these. And the algorithms can be applied in different domains with different instantiations related to the environment, to the task, and to the safety involved in each of them. So this is what we are doing at SRC, which was launched in November 1st, 2024. And it attracted.
The center idea is really about how can we bring an environment for collaboration.
I just said that. So anyway, the idea is really to bring this collaboration, but how can you do it? You need an environment, you need shared robotic projects, and this is what we managed to do in the center with a lot of different spaces dedicated to different things from art. In fact, yesterday we had art and robots performance just before I left. We have field robotics, we have different aspects of medical robotic applications, we have human robot interactions, we have so many different areas that are all being addressed. These are different interfaces, and we have also collaboration with different international laboratories. This is with the Karlsruhe Institute of Technology. There is also collaboration with IIT. There are a lot of involvement of material and design of tactile sensing to build skins. There is a lot of beautiful ideas coming in minimally invasive surgeries. So now my dream was always to recreate artificial potential fits, but actually with magnet. And now we have magnets controlling robots to move, and this robot can be used to deliver medicine, but also to do surgery. This is an example of surgery in the brain, and the robot is guiding the magnetic field to move this spinner to those locations. This is a very, very exciting project taking place. Another one I will talk about later about ultrasound. We are also advancing with new ideas about how we do minimally invasive surgeries. I mentioned art, and we are not just about performing, but about understanding human motion, connecting it to robotic motion, looking at energy and different characteristics. How come human spends so little energy compared to robots, and how we can use robot in social context to assist, to work with kids with problems, and in the kitchen, etc. Amazing environment to create this bridge between research and the real world, with support of industry. And we have a lot of visitors now. That is the problem. It's becoming the San Francisco exploratorium of robotics. And Stanford, seriously, I mean, we have so many visitors that we hired the robot to do the visits, which is good. But we have a lot of support now just to handle the tours. So this is a little bit about the Robotics Center, and I hope you will have the chance to stop there when you visit Stanford in the future. Okay, about the talk. So I'm going to go over a lot of things that we have been working on recently, and also take a historical perspective of those things and how things are working in the context of today's robotics. So deep sea is actually very similar to the challenges in healthcare, in the workplace. There are some common things about human-robot interaction, human-robot collaboration, and how we can bring the proper interfaces to work together with machines. So here is a short clip.
OceanOneK, a unique underwater robot capable of carrying out archaeological excavations several hundred meters beneath the sea. Since 2015, an American team has been developing this revolutionary humanoid. The objective is to be able to explore shipwrecks, handle relics, evaluate and study treasures with the same precision as archaeologists.
Today, robots are designed to see, but we need robots that are designed to do.
This research would enable archaeologists to excavate countless wrecks of warships, merchant ships, aircraft, and submarines from every era that have up until now been totally inaccessible. But how can we be sure that Ocean One will withstand the extreme pressures? Or that its bionic hands will be able to recover sunken objects from the abyss?
This is really the introduction of a documentary film about the expedition that we had in the Mediterranean over 2021, 2022. If you remember, this was really in the middle of COVID, and it was really, really challenging to get all the certification, to build things, to go to the lab, to do expeditions. But we managed to do it, going all the way from 40 meters to almost 1,000 meter through amazing spaces. This is a Roman boat lost almost 2,000 years ago. This is from the period of the Second World War, and with incredible marine biology and corals. And then the test for us was, can we go and take a robot and operate at very, very deep depth? And we were limited by the thrusters that were qualified to 850 meters. So we went to 852 meters. We didn't break anything, but it was an amazing challenge to build a machine that can do that. So the key in all of this is of course, the control room. So you have haptic devices, and with these haptic devices, your hands are connected to the hands of the robot, and your eyes are connected to the eyes of the robot. So your eyes are in the water with your hands in the water, and you are almost there, except you're not getting wet. Now, if we think about a task like this one, you're placing this marker to do the scan of the boat, and you have to place the hook on the rail. You are going to need to get sensing of your forces, and that contact is completely reflected here. You see, this is the rail. You don't see it properly because it's in stereo. And once you wear the glasses, you see the stereo, of course. And then you are able to see it and feel it, and you touch. It's electrical. The year after, we took the robot to deep dive. This is the deepest pool in the world, in Dubai. And the robot, you can see through, so it's really, really amazing. And deep dive provides this environment to play, to work. And play is very important for robots, as you know. So robots are playing here. The robot is playing and winning. And here is a short video about that short expedition. Checkmate. Have you seen a robot playing underwater chess? So the robot has also capability to read, and you can see that clearly with the eyes of the robot reading the. So, what is different with this robot is, of course, we have many underwater vehicles that can go much deeper, and they can go and also explore and bring a lot of amazing images. Most of those vehicles have little small abilities to manipulate, because they have limited gripper that requires the motion of the whole robot in order to perform the task. So if you have a task like this that requires touching and feeling and really interacting with dexterity, then you need to have a robot that has those capabilities. You need hands, you need arms that carries the hands, and you need a body that carries the arms, and you need to see your hands, so you need to see with also depth, so you need stereo. So this was the concept, basically. Now, how do you build the robot? Well, you need to think about the design of the robot. In the beginning, we had the arms on the top. Then you have so you need to have realistic simulation. But realistic simulation requires also to design and think about the interaction, the physical contact with the environment. And this means you are building a system where you are able to touch what the robot is touching. You push, you feel it. So that requires haptic connection. And this idea, archaeologists don't want to remove anything before touching it and feeling and making sure it is movable. And there is a lot of cognitive decisions that need to be done by human, and you need to build as much autonomy as you can in the robot side. What you don't see is this. So what you don't see is the dynamics involved as you approach. When you look at this robot, you see these we call them bolted ellipsoid. Bolted ellipsoid represent the actual effective masses and inertias reflected at the end effector. And when you bring them together, you change the dynamic again. And what is really, this is the augmented object produced by the sum of all the inertial forces. But what is important is realize that if your arm is extended, you are going to feel the body of the robot at contact. So you better know where to put your posture and how you approach object and how you make sure that you are not going to create impact forces, large impact forces on the object you're manipulating. So in 2016, we had the first version of the robot ready. Oh, this is the simulation, the training environment. It's like a flight simulator, but really for underwater robots. And we tested the robot in the pool at Stanford, took the robot to the Mediterranean, and deployed the robot on La Lune, a vessel of King Louis XIV, lost in 1664. And it was amazing. We recovered a Catalan vase, a beautiful Catalan vase that the archaeologists couldn't really reach, and it is amazing in the fact that it came in one piece. We didn't scratch it, we didn't damage it, and that was a big news in the archaeology circles, and brought a lot of interest in this technology, declared as the best technology since Jacques Cousteau's work in bringing technology for underwater exploration. Archaeology is not the only thing you can do. Of course, you can support scientists. We were in missions with scientists on the volcano of the Colombo volcano in Santorini. And of course, all the work and maintenance of operations of all the structures human built underwater that are not maintained, and as a result we have a lot of accident. And also, if we think about it, they build structures very deep. Human can dive how deep? Any diver here? How deep? 60 meters, 40, 50? Yeah, so the average depth of the sea is 3,500 meters. What can we do? And we have really, and the structures like this are at 3,000 meters. So they go and when there is really a problem, they have to lift it up and stop the production and redo everything. What about the corals? I mean, what about all the life in the oceans that we know maybe more about Mars than our own ocean, and there is, so every mission we had marine biologists, archaeologists, and it was amazing to be able to be with them and work and discover things and move, and so you have this ability to really do work at depth and and be almost there without, providing this ability to bring the human eyes and senses to that environment. Well, this is not limited to just the underwater robotics. I mean, we're doing the same thing for medical robotics. So ultrasound imaging can be benefiting a lot from those interfaces because sonographers are really rare these days. And so, this work for radiologists is very bad for the wrist. It damaged the wrist after like years of work. And having a more comfortable way of doing the task is a fantastic thing. But now you have the image, you have the patient. This is a very expensive phantom that we are using with all kind of diseases and all the organs in the body of that phantom. Now, here is the radiologist. They don't need to be in the same room. They can be in different buildings, different countries, different continent. And in fact, this is a new also extension of what we can do with robotics and input from a radiologist, a doctor at distance. We know we can connect through vision and voice, but can we connect contact, physical information? Well, if we do that, we are doing teleoperation. Well, we know with teleoperation, delay causes a problem of stability in the system. You are taking the feedback and returning it, and this is going to cause instability, time delay. So what can we do? Well, do we really need to have it in one feedback loop? Why don't we build two autonomous systems communicating set point, input, information? And that changes completely the problem. We go from like limited, like 150 milliseconds to 1 second without any difficulty. And imagine what we can do now for all these villages that has no access to hospitals. We can have a doctor thousands of miles away where the robot with a technician in the village performing that operation. So this is almost a sort of like, you would think about it like a dream, because we're talking about going beyond just the communication of the visuals, but getting to do the contact. And in fact, if we do this, then we can have a network all around the world to connect these maybe mobile clinics with a simple robot, and the driver technician can put the gel and place the patient, but now you're connected to the hospital that will perform the whole task. Well, we did this test from Abu Dhabi, not to do the ultrasound imaging, but to connect and feel contact everywhere around the planet. And this, you can see from the right, the left, Stanford, Korea, and then from the other side, you have Singapore and Germany. So we did the test with the ultrasound imaging. So I became a radiologist with the princess of Thailand that you see here, and she was trying the haptic device, and we were performing live from Bangkok all the way back to Stanford. So this is the image in Stanford, basically connecting Bangkok to Stanford. So in Stanford, my students were at 3 a.m, like waiting for the session to start. And this radiologist here is maneuvering the sensor to find these high density material. I know exactly where they are in the liver, and I was just moving from like remotely to touch and feel and do this whole task. So it is becoming really possible, the convergence of technology in robotics with the convergence of technologies from interfaces and communication and the algorithms, all of these are enabling us to do things that we really couldn't do before. So it's sort of like, from the example of going to the ocean or to the fire or to the mine, to all the medical application, we are distancing the human, or we're using the distance to our advantage, but because we are reconnecting the human skills. And this is very, very critical. You want as much autonomy on the side of the robot, but the robot is your sensor in the water. You need to get that information back to a human to make the next decision. So using the internet is that provided always ways to hear and see. Now we can touch and feel. And you could imagine all kind of network that can be built around this with machines and robots for many applications. In the medical applications, there is a permanent concern about safety. And we have been dealing with safety for many years in the robotics field. I mean, especially after the turn of the century, when we started really building more and more medical application, robots for medical application, there was a number of workshops and efforts to address the fact that we need really to deal with safety. So safety can be achieved with software, with control safety, with many aspects of this. But who can guarantee that software safety is going to be 100% reliable? Or the control or whatever we do without really dealing with the hardware itself. So the first thing we need to do is really to deal with the compliance of the robot, make it as light as possible. And over the years, we built different machines. And finally, I've been working on a new design that will really bring us closer and closer to complete safety. So this design is, well, the robot is called Maestro. And Maestro comes from a long story of development that started in the mid-90s. We worked with a robot called Artisan, and Artisan was a robot that was the predecessor to LWR, the DLR robot. As we started working on Artisan, we had a collaboration with DLR, with Gerd Herzinger, and we saw this robot becoming the KUKA robot. The EVA was the LWR that moved to KUKA, and that technology continued with Franca, and more recently the Flexif brought also a similar. So the key here is torque control. Torque control removes all the perception of the gear transmission system, and you have a pure source of torque, and now you can do a good interaction manipulation and very, very good safety. But safety is not yet 100% because you rely on that everything is going to work with the control and the software. And then you have all kind of issues with those mechanisms that are not really, you see all these offset, they don't have intersecting axes. And if we study the problems of linear motion, angular motion, we see that then we are going to, just to rotate an object, we have to do a large motion of the body of the robot. So Maestro addresses all of these with amazing compactness. I don't know how we managed to bring it so compact compared to the KUKA design, with 3 intersecting axes, with no singularity in the wrist, which is really, really important, and also with full safety. So let's take this example. We have the patient and we have the robot, and we are going to tell the robot, you have a barrier, don't go beyond, otherwise you might hurt our patient. So you look at the workspace, this is your workspace, and you see the workspace is intersecting with the human. But then I mean, you have software and sensors will prevent the robot from going beyond. Well, I'm not satisfied. I want to make it passive. I want the robot to be. I need a robot that has a different workspace, separated from the human, not intersecting with the human. So let's go and buy another robot, or let's go and change the way we design it. When we design the robot, we design, of course, the workspace. How do we design the workspace? With joint limits, right? Okay, let's change the joint limits actively before the procedure. We're going to add a module, and this module is going to reconfigure the joint limits, and now your workspace that was like this becomes like this. So now the robot it's like a different robot for every task and every patient, and gives you 100% guarantee, because you have to break the robot in order to reach beyond that configuration. So all these applications now can benefit. I mean, we have a lot of works and applications in different areas, and you can see how you can protect environment sensitive areas, and how also you can, through the interaction, you can create minimally invasive mining, I call it. So this is a snake-like robot that is going inside and just extracting what is needed, not removing everything and using very difficult environment, and then also toxic chemicals that result at the end for the extraction. In space, we already placed the haptic devices, and we are controlling robot on the ground. So a lot of progress connecting human to the machine. So in the history of all of this, let me just give you a small, very brief history from the side of the things that we were doing at Stanford. How many of you remember Romeo and Juliet? I'm sure not many remember Romeo and Juliet. So let me show you Romeo and Juliet. Romeo and Juliet were inaugurating the Gates building at Stanford in the mid 90s. And I'm showing this because there is really a big message about these robots. Vacuuming, ironing, collaboration between two mobile robots. This is even very difficult today. How come we were able to do it? What is the secret? I mean, how this was implemented later on humans models, musculoskeletal models, and on Asimo that spent 12 years at Stanford, and that became compliant. And that's what led to the project to go with humanoid underwater. And all of these were sort of really beyond what we can imagine in terms of how can we control robot by designing, planning trajectories of joint motion and doing the interactions. So this is the first version of Asimo, of OceanOneK at Stanford before diving in the Mediterranean almost 10 years ago. Actually, today is what day? 15? 13. So next week we will celebrate 10 years. So this is the recovering of the vase. Oh, 15th, yeah, April. That's good. So this is the famous Catalan vase. Now, how we control robots? Do we compute all the joint motions for this task of tracking a red ball? I mean, this is what most people do. You try to find some trajectories and you track, you control your joints to perform that motion. There is no trajectory whatsoever for the robot, except the robot is trying with the hand to reach through some sort of force. I mean, simplify, like you have a potential energy pulling you to the goal. And the body has another criterion, another potential energy, telling the body to maximize the range of motion of the arm or to keep it as far away as possible from the joint limits or as close as possible to the mid-range. It's just a gradient of potential energy, two gradient of potential energies. No trajectories, no inverse kinematics, nothing. Because we have this relation, torque equals J transpose F, and you can think about the null space of J transpose, and then now with the two, you can control the task, and in the null space, you control the posture. So this is the basis for allowing us to go further and control contact. How do we control contact? The environment is moving. There is a compliant frame. And the compliant frame is using a human strategy we don't think about, which is to take a compliant point at the center of the centroid of the object, little bit beneath. And this centroid is going to create zero moment about the two axes and a force. And we don't care where the object is. And this is how you can perform complex tasks just by simple strategies. So human skills are amazing. And can we extract human skills, not human motion-induced trajectories? We want to understand what is beyond the motion. And to do this for manipulation is fantastic, because this is where robotics is really having trouble. We are facing a lot of challenges with programming robot for skills, and we really need to understand those skills and put more effort on it. So we're going to use learning, but not to record trajectories, because record trajectories will never work in contact, for rigid contact and object with any level of rigidity. What you want to do is you want to find this compliant frame. And the compliant frame is there. What is compliant frame? It means in some direction I have space to move, and other directions I cannot move, but I exert forces. And determining that is going to allow us to reproduce what the human strategy in performing the task was. So after segmentation, we're not going just to take an image and connect it to action. We need to understand what was going on. And when we record data, we record force and motion, velocity, data. And when you have zero velocity in a direction, you see increased force, you know what is happening. And this is both for linear and angular motion. And now you have your strategy. And you throw away all the data, because now it is independent even of the robot. The data is related to the task. And if you want to understand the behavior for the posture, you have different data, and you can capture it also with a criterion based on energies that you can create for the self-motion. And then you can do the execution. So here are some examples where we learn strategy. This is a piece of the wing of 787 with a task, and you disturb the robot, and the robot is executing a sequence with those compliant motion. Disturb it again, and the robot will execute the sequence and do it again. Here, your vision doesn't help you to grasp, so you need to touch and feel and find the normals to grasp, and then you will be able to execute the motion. This is other examples. Actually, you teach the robot the strategy of putting a teacup. Now, of course, there are many aspects of those problems, how we cross between different geometries and material properties. But we need also the platform for the software, the simulation. What is difficult in simulation? I mean, everything is amazing. I mean, we have a lot of simulation systems today. But one thing about Psi that is unique, and this is multi-point, multi-collision that takes place between all these multiple links. How can we resolve that in real time? If you really want to interact with the simulation. So from the time, the mid-90s, we developed an algorithm and we kept improving it. And you can see all these object and humanoid are colliding at multiple points. And this was done in real time. So what is the secret? What is the secret in this? I mentioned something about controlling the end effector in operational space. How we do this? We project the dynamics at a frame here. If you have a collision here, you can project the dynamics at a collision here. If you don't believe me, ask him. Basically, it is thinking about not how I'm moving here, but how the combination is going to produce an effective mass at this point. You project the dynamic here, you project the dynamic here, you have two masses now colliding. And this is the key to creating algorithms that are efficient to solving multi-point collision of multi-link systems. So this is in our Psi system, and recently, and you are welcome to check OpenPsi and have access to that framework. It has the control in operational space. It has every aspect of the work that you need, and it implements the architecture. Robotics is not about just like having one loop connecting what I see with action. It is a multi-loop system that takes us through the frequency domain. The frequency domain is critical. At the mechanical level, controlling the robot, you need to go to kilohertz. But the input is much slower, and that input is a skill that requires also to extract features. So it's naturally going to work at a much slower level to send those skills parameters to the controller. And as we move up, we slow down those closed loops. So it's a multi-layer loops that allow us to create this autonomy for the system. But it's only functional autonomy. Grasping, manipulating, but where is the cognitive autonomy? This is a question, it's hidden. We talk autonomy, my robot is autonomous, but we have autonomous car, but what is challenging is to understand the intention of the other driver. We have to make decisions in surgery or in operations, complex operation, and those requires experience, expertise, intuition, a lot of things. And that's why we need the interface to the human. And that's how we can really do real things. So our students actually are using this in a class we teach called experimental robotics. And the students are able to do these projects in 3 weeks. Given the framework, given the environment, the robots, look at this. No cameras, only the force sensor. And these are students who just like went through the course, and then they get the software and they create a project. This is very slippery. So during COVID, we couldn't go to the lab, but we gave them that environment of simulation and control. And these are physically controlled. Seriously, I mean, they are controlled with the same architecture and physically correct, except when a robot gets angry, you never know what happens. All right, let's go back to Ocean One. So Ocean One was built during COVID, and we were testing the robot in the pool to do different tasks, preparing the robot with preparing the camera use, and we get the robot to the La Ciotta where the robot was going to dive, and here is the equipment, because a robot is not going to dive alone. You need to put cameras, you need to put light, and here is the control room. I explained how you are connected to the robot. What you see is this image. You don't see more. So we have other other displays from other robots filming the robot, so you see the context. And we went down to submarines and to the area, and look what we brought back. These are objects from 2,000 years sitting at 350 meters, oil lamps with different decoration, and amazing like marine biology samples that we couldn't access. And finally, the robot kept going to 500 meters and filming inside the boat using the camera, and then went to Cannes, diving all the way to the bottom of the sea, carrying a message. And here is the short video that I mentioned. Yeah.
In the course of 5 dives in the Mediterranean, OceanOneK will be pushed to its limits and attempt to reach a depth of 850 meters. As the sun rises over the port of Bastia, OceanOneK sets off for its next challenge at a site well known to archaeologists, a wreck known as Area 1.
So this is part of a long film that is a documentary, and it is not yet public. So that's why we had to just turn the recording. But it was an incredible mission in that. We design in our lab, we do things, but when you go to the field, you are facing so many challenges, and not the film and not me is going to tell you about all the failures and the stuff that took us finally to achieve this. This is the team, and it is really an incredible team of a crew that was every day excited. I mean, this lasted over maybe few weeks in 2021 and few weeks in 2022, involving all these people and my student and collaborators. It was really a great expedition, and the students are just waiting for the next one. Thank you very much for your attention. Thank you.
Time for one or two quick questions. Yeah, in the back. So humans are usually like not optimized to go underwater, right? So why do you decide to like make it look like a human?
Yeah, thank you for this question. In any unstructured environment, you need two hands. you don't have fixtures like in manufacturing, so you need a hand like to help you take objects and right. So you need two arms to carry the hands, right? You need to see your hands. You need two eyes. You need to see depth. You need stereo, and you need to carry everything in a mechanism. Now, you don't have to make the head look like a human head. You can have it like with whatever shape you would like. But you remember that this is also guided by a human. All the archaeologists who worked and interacted with those environments felt like so natural. It is just like you are diving and you are in that posture and you are performing. So when you try it, it's so intuitive, so easy. But I mean, I don't have anything against designing it differently with some more abstract form, except the fact that also we are using the fact that we have the head to fill it with flotation so that we can move the head with small motors in the back. Now, the other challenge is we are also interacting with other like divers, because like it's support to scientists and others working underwater. So they always felt he is following me. He's doing like they talk about it like something like another colleague. So, but you can consider other concepts for the shape, but you still need all these functionalities.
Yes. So 850 meters is just spectacular. But what's your next mission?
Thank you for this question. Well, we never stop. We keep going, right? So the good news is the foam we are using, which is my hollow microsphere, can go up to 5,000 meters. This is the flotation. I mean, what yeah, we didn't mention it. We didn't have time to talk about it, but essentially we have a floating robot. It's flying in the water, and the thrusters and everything really lightweight, but you can do a lot of tasks. If you have to carry the load, it would be huge, very heavy, like shelling arms. And if you are using metal like the shelling arms, then I mean it's a completely different story. So what we use is very gentle arms that have oil inside, which is the same pressure as the pressure where you are. And this is through compensators and things. So there are a lot of technologies that are used, and all these technologies are valid to take us to 5,000 meters. So next we are going to go to, probably we will go to 4,000 meters, because the problem after 4,000 you start to have variation in the density of the water, and that's a different problem. So we don't, and the Titanic is only at 3,800, so we don't need to go there. But the design of Maestro will be used in that robot. So the robot will be smaller, lighter, and more compact, and it is hopefully will be also in collaboration with MIT Woods Hole Center, and we are working now on building the robot and planning all the other missions.
So, but the Titanic is old news. I mean,
Yeah.
it's been there. What about going to Midway?
Yeah, well, the robot actually, our robot is overbooked already. So in few weeks, like 3 weeks, we are sending the robot to Singapore to dive in the aquarium there in Sentosa, and it is going to be a lot of fun. I like the robot when you can see it, and the cool thing, we develop all the control, all the tests in the pool at 1.5 meter, and it works at like 1,000 meters. It doesn't matter the depth. It is the only thing we have to do is to recalibrate the buoyancy for the sea. The sea, you have more lifting, and you have like different things. The new robot will have some compensation also for the changes in the center of buoyancy. You want always the center buoyancy to be coincident with the center of mass, and that's something that is not always perfect. You move your arms, so we have to combine the two, and that's why we are adding few features. But mostly the technologies are there. It's a matter now of integration.
So in the interest of time, I know there are more questions, but we also have a social afterwards. So in interest of time, let's thank the speaker again. Thank you, Oussama, for the wonderful talk.
Thank you very much. Thank you.